Acids and bases are two very important groups of compounds in chemistry. They are responsible for some of the different tastes that we experience in our food and through other substances. We use them for cleaning products. We use them for etching. There's a variety of different ways that we use acids and bases. They're important in our biological systems. As far as a certain level of acids and bases have to be maintained within the body. Too much acid or too much base is damaging to the body systems as well. And acids are responsible in certain cases for unfolding proteins in the body and disrupting enzymatic activity. We see these things in people that have consumed too much alcohol, long-term damage. As well as people experiencing various other problems with maintaining the appropriate acid level in their blood. So first of all, let's ask ourselves, what are some of the general properties of what we call acids and bases? So we're going to set up a little table here. So we'll have acids here, and then we'll have bases here. And then we'll have the properties. Okay, the first property is that of taste. All acids are detected by the tongue as having sour taste. So anything that you eat or consume that tastes sour to you is so because you're consuming an acid. For example, pickles are created using the acid acetic acid, which is also known as vinegar. If you like candies like Sour Patch Kids and Sour Jolly Ranchers, those types of things, those contain citric acid. That's a dried form of the same acid that's present in most of our citrus fruits, oranges, lemons, limes, and grapefruits, which also give the sour taste. Bases, on the other hand, are detected by the tongue as being bitter. If you were ever a child and you said a bad word and your mommy washed your mouth out with soap, that bad taste you get when you get soap or shampoo or something in your mouth, that bitter, nasty taste comes from the fact that those substances contain bases. Okay, the next property is how do these feel? How do our the nerves in our skin react to the presence of acids and bases? Acids tend to feel a little rough, and prolonged contact or contact with highly concentrated or what we call strong acids, which we'll talk about in a little bit, also is a burning sensation. A lot of skin damage can occur upon contact with certain acids. You can certainly put your finger in the jar of pickle juice and it's not going to cause damage unless it's a long-term contact. Bases, on the other hand, tend to feel slippery. That sensation we get with soap or shampoo or other things, as far as they're being very slippery, comes from the fact that they contain bases. Okay, the next property is their conductivity. Both acids and bases are good conductors of electricity. In fact, both of them contain what we call charged particles or ions that allow the electrical current to pass through the substance easily with very little what we call resistance. Okay, the next property is reactivity with metals. Most acids are generally good reactors with metals. most cases they produce hydrogen gas and dissolve the metal that's in contact with them. This is used in the etching process, and a lot of times we try to counteract reactivity with metals by plating over the top of a metal with another metal that is less reactive with acids in order to protect them as perhaps a softer or more active metal underneath. Bases do not react well with metals. That's poor reactivity. Our last property is something called the litmus test. Litmus is what we call an acid-base indicator. We'll come back to that in a couple of sections. An indicator is itself a weak acid that actually changes color depending on whether it comes into contact with other acids or with bases instead. So the litmus, when it comes into contact with acid, is red, and it comes into contact with a base is blue. Okay, so that's just a general description of these two groups of compounds. Next we're going to look at how do we know from a chemical standpoint, well, what substances are acids and what substances are bases. So we're going to look at two different models or descriptions of what makes a substance an acid or a base. The first one is the Arrhenius model. Sorry, I'm not very good to draw with a straight line here. And the other model is called Bronsted-Lowry, or BL for short. Okay, the Arrhenius model of an acid are substances that produce hydrogen ions. In water. Sorry about that. Okay, so we can recognize an acid because there's a hydrogen at the beginning of the formula. Okay, so all of the acids that you learned back in the nomenclature chapter, they're acids because Arrhenius defines an acid as a substance that produces hydrogen ions in water. So what this means is that when you put HCl into water, remember acids are aqueous substances, it means that it's going to dissociate. And they'll break apart as ionic compounds with H plus and the rest of it is Cl minus. So this is a general form of dissociation of an acid. So it's HA makes H plus plus A minus. The A is just whatever is the remainder of the, what's the negative ion that the hydrogen is attached to. So what's a base according to Arrhenius? Okay. The Arrhenius definition of a base is that a base are substances that produce hydroxide ions when they're placed into water. So that means that any substance that you would call a hydroxide would be considered a base. That's what we're looking at. Okay, so potassium hydroxide, sodium hydroxide, etc., those are all considered the bases. Okay, the Bronsted-Lowry model describes what makes an acid or a base in a different way, and in doing so dramatically expands the umbrella that covers acids and bases. So substances that the Arrhenius definition covers certain substances. The Bronsted-Lowry covers more substances than the Arrhenius definition does, especially when it comes to bases. Okay, so how does the Bronsted-Lowry model different? The Bronsted-Lowry model defines acid as substances that can donate a proton. Now, when you get right down to it, a hydrogen ion is a proton because a hydrogen atom contains one proton in the nucleus and one electron orbiting the nucleus. And if you take off the electron and make it plus, all that's left is the proton, which is the only thing in the nucleus for a hydrogen, most hydrogen atoms. So by saying an acid can donate a proton, what's it really donating? It's donating H+. So the general form of Bronsted-Lowry looks really similar to the definition under Arrhenius. So just a little bit different way of describing the same thing. So how are bases different? Well, here's where we're looking at some real differences. Under the Bronsted-Lowry model, bases are defined as substances that can accept a proton. So that means that B now that doesn't look the same. Okay, so in this case, a base can be any substance, charged or not, that has the ability to accept a proton, in which case this would be a general way of describing its formula. So let's look at something specific here. This is a base, NH3. The IUPAC nomenclature says that we will call that nitrogen trihydride. However, like H2O, it has a common name that it's usually used, and which would be ammonia. So NH3 is ammonia. Now, when NH3 accepts H+, because it is a Bronsted-Lowry base, but not an Arrhenius base, it becomes the ammonium ion. So this is a base because it can accept a proton and become the ammonium ion. So Bronsted-Lowry's and Arrhenius models of acids are very, very similar. Any substance is an Arrhenius acid is also a Bronsted-Lowry acid, and vice versa. However, the big difference between these two definitions is that the Arrhenius model says that bases produce OH-, in other words, they are compounds that contain the hydroxide ion to begin with, whereas Bronsted-Lowry says a base can accept a proton. Now, Bronsted-Lowry bases do cover the Arrhenius bases because, from an Arrhenius standpoint, this is really the base, the OH-, because OH- could accept an H+, in which case it would become water. So even though the two models are somewhat different, okay, they're both describing, to a certain extent, the same process. The Bronsted-Lowry model, especially for bases, is just a very broader description and covers more compounds. Okay, the last thing in this section is strength. Now this is an important concept because we come into contact with acids and bases on a regular basis. Okay, most of us are familiar with the acid that's in our stomach, hydrochloric acid. And most of us, unfortunately, are probably experienced the unpleasant sensation during vomiting of the burning sensation that comes from the hydrochloric acid in the stomach being expelled through the esophagus. That gives that horrible sour taste to vomit. It can also kind of cause burning. People that suffer from bulimia, which is an eating disorder where people consume large quantities of food and then vomit it up immediately, tends to give people a lot of dental problems and mouth problems because the constant passing of the stomach contents, which have a lot of hydrochloric acid in them, over the enamel of the teeth or the mouth, eventually they tend to wear off the enamel and they have a lot of tooth problems. Now, however, it's contained in our stomach, but we don't want to drink hydrochloric acid. However, we're quite happy to drink cider. Cranberry juice is high in acid. So what's the difference? I mean, you wouldn't drink battery acid. We all know that's really, really bad for you. So what makes some acids somehow seem to be more dangerous or more likely to cause damage to biological tissue than others? And it comes down to their strength. Now strength, the first thing you have to note for yourself is that strength does not the same as concentrated. Now it is true that you concentrated acids or bases do pose greater risks. However, you can have concentrated strong acids and concentrated weak acids. Okay, concentrated strong acids can be dangerous, but dilute strong acids can also be very dangerous. So strength does not equal concentration. Well, then what do we talk about? We talk about strength. Strength equals is the ability of the acid or base to easily dissociate. So for example, if you have 100 hydrochloric acid molecules, 100 HCl, and you stick them in water, okay, what you're going to get is 100 H plus and 100 Cl minus. However, if you take 100 acetic acid molecules, then you stick them with water, you'll get probably 5H plus 5 acetate ions and 95 undissociated molecules. So hydrochloric acid, almost 100% of every molecule of hydrochloric acid will break apart. So you get a large amount of of the H plus, the hydrogen ions. And that's what's responsible for all the properties we're talking about. Okay? The burning, the sour taste. And if you compare that to our acetic acid molecules, we get very few hydrogen ions out of this exact same amount of acid. Okay? You get all this acid floating around that's not dissociated. And if it's not dissociated, it doesn't have any acidic properties. So how do we just know, is there any way to know which acids are strong, which acids are weak, and which bases are strong and which bases are weak? And the answer is yes. The acids, there are 6 strong ones. They are HCl, HBr, HI, but not HF. So basically the halogenic acids, but not hydrogen fluoride. Okay. Hydrofluoric acid is not a strong acid, it's a weak acid. Okay. Sulfuric acid, H2SO4, also known as battery acid. Perchloric acid. Okay, part of this is you find in your Clorox bleach. And nitric acid. So any acid that is not on this list is a weak acid. You simply have to memorize, unfortunately, the strong acids. So what are the strong bases? All hydroxides are considered strong bases. So NaOH, MgOH2, AlOH3, all of those are strong bases. So in other words, all the Arrhenius bases are strong bases. Okay. Since the Bronsted-Lowry model is much broader, there are most of your weak bases, in fact all of your weak bases, are Bronsted-Lowry bases that would not be considered bases underneath the Arrhenius model. So that's how we determine what is a strong acid and what is a weak acid.